I work in the area of computational science and engineering. And in computational science and engineering, we use the computer to solve problems from science and engineering. And we develop new methodologies for simulating more and more complex phenomena. So my research has had several generations of different areas. And when I first started in this area, I was working for a long time on methods for solving differential equations on the computer. Now, just about everything that moves is describable by a system of differential equations. So this has a lot of practical relevance. For example, suppose you were a car company and you were designing a new car, and you would like to see, does it have a smooth ride? Then you can model all of the mechanical components in the car, including the suspension system. And you can see on the computer what it will result in, what kind of a ride it will result in. You can actually make a contraption that will let you feel that. And why is this important, to our country, to the world, to car companies, so that you can run through many designs, because you don't have to take the time to actually build them. You can see what they're going to look like in minutes on the computer. Some of my work, I know, has been used in the design of washing machines. So that if you put the heavy rug in the washing machine, should it give that nasty buzzy sound, or should it do something smart and jiggle the bin so that it doesn't have to bother you about that? In recent years, I've been working in a little bit different area. I've been working in multi-scale and discrete stochastic simulation, and a lot of that work is motivated by problems in systems biology. So systems biology studies biology, mostly cell biology, from a systems level perspective. So instead of looking at all the individual pieces and trying to deduce piece by piece how things are built, it looks more like a systems engineer would look at it, more like you would look at the outputs, what the organism is doing, and sort of from both perspectives, from the really important knowledge that biologists have so painstakingly developed over the years of how the components work, the genes and the proteins, together with all the knowledge that you can now get from high throughput experiments where you get thousands, tens of thousands pieces of information at once. So you can't just go hypothesis, conclusion. You've got lots of information you need to integrate. The only way to do that really is with a mathematical model, and the model is so complicated that it has to be done on a computer. There are many processes that go on, for example, inside of cells, where there are molecules that are present in very small quantities. For example, DNA. That's the simplest example that we all know about. And when there are molecules that are present in very small quantities, if they're key molecules, sometimes they're key molecules that can change the outcome for that cell, can change it to do something different, to live or die, to move away or to come closer, things like that. Then those become what we call stochastic processes. They depend on chance. Did these two molecules get close together at the right time and things like that. And so we use stochastic models, random models with probabilities of different kinds of events and chemical reactions to happen. So that takes a tremendous amount of computer time to get good estimates, because you have to run a great many stochastic models to get overall probabilities. And that's where somebody like me comes in. Basically, I build the infrastructure for people to do modeling. Well, we're looking at a lot of applications, mostly, some from fundamental biology. Okay, so I have a project on polarization in yeast mating. So you may not know that sometimes yeast shells don't just divide, they mate. And they need to sense the pheromone gradients of the potential mate, and orient themselves towards that mate and start growing an appendage in that direction. And how does that happen? And how does all that biological material move in order to grow the appendage? And how does it do that so accurately? And what happens if another potential mate, a better one, comes by? How does it move, track that one, and lose the other one? So that's some fundamental biology. I've also got projects in my group on understanding post-traumatic stress disorder and understanding coagulopathy, what happens when you're in a very bad freeway accident and you have multiple injuries and your blood starts failing to coagulate properly, and what are the mechanisms, the chemical mechanisms that drive these kinds of processes. And obviously, ultimately, we're looking for the targets that you would target drug interventions. It is really amazing. When Toshi called me, I was really excited. I was like, "You're kidding!" I was surprised for sure. I'm deeply honored. I've had many awards, but I think this one is very special because it comes from my colleagues who I work with every day, and many who I don't know, but I know do tremendously good work. To be recognized by the people, not only in your own profession, but in your own institution, I think is very special.